So I made a Minecraft shader with distant horizon support, screen space reflections, and shadows. Join me as I code the shader and learn everything you need to know to make your own. And I'll show you how to support distant horizons. We're going to use Visual Studio Code for the coding, and these extensions will help us code. Let's download the universal jar from Iris Shaders. Let's install the latest version of Iris plus Fabric. Now we just open up the Minecraft launcher, watch this little armadillo run around, and this latest installed version will be the one. Go to Installations folder, open the Mods folder, go to Modrinth and search Distant Horizons, and let's download the 1.20.6 version. Make sure to grab Indium as well. Grab the Fabric API and drag the mods you just downloaded to the mods folder. Make sure to give Minecraft some extra RAM. It's going to need it for distant horizons. Make sure to have this toggled because this will be very helpful when it comes to debugging. We will keep the default settings for distant horizons. Now if we load into a world, and there we go, that is distant horizons. And it's going to get better as it loads everything in. But we're here to make a shader pack. So we're going to head to Options, Video Settings, Shader Packs, and open Shader Pack folder. Just right click, New Folder, and name it whatever you want to name your shader pack. I need to come up with a good name here. Daybreak. No results. That's good. So I'm going to name my shader Daybreak. And would you look at that? We have a shader and we're all done. There we go. We are now running our beautiful shader that has literally no code in it. As you probably thought, inside the Daybreak folder, we should add something. Create another new folder and name this one Shaders. In Shaders, let's add a text document, but it's not actually going to be a text document. We're going to change the extension and let's name it gbuffers_basic VSH. Yes, we know what we're doing. That stands for vertex shader, and I'll explain what that is soon. Copy that, paste it, and let's name this one gbuffersbasic.fsh. That stands for fragment shader. Now in VS Code, we can open a folder, go to our shaders folder, copy the path, paste it here, and select folder. This is our folder, and these are both our files, our beautiful empty files. The first thing to add is the version of GLSL we'll be using. GLSL, it's a language designed specifically to run on the GPU, and 460, as of the time of this video, is the latest version. Next, we're going to have the main function, so we say void main, 2 parentheses, and brackets. This is our main function, which will be automatically run each time this shader is called. And we have void just because this function is automatically set up to not return anything. These parentheses are here for our inputs, but there's no inputs expected for the main function. Let's copy this and paste it into the fragment shader as well. Now back in the vertex shader, let's get some data. Now it's time to use a resource, which is the Optifine Doc. This gives you all sorts of information about how Optifine and Iris work. Everything we'll be doing in this video will mostly work with Optifine as well as Iris, but eventually we'll start adding some Iris-specific features, like distant horizons. Everything that works in Optifine also works in Iris, so the Optifine Doc is really useful for both. Now the first thing we want to add is the vaPosition, which is the position of every vertex. So let's put that here above the main function. We're taking this into the program, and this is a vector 3, which means it is a set of 3 values which are an x, y, and z coordinate in 3D space. If I open Blender real fast, a vertex is every dot that is used to make up an object. Vertices are connected to form triangles, which are then used to render any object. So everything in a game is made up of vertices. vaPosition will give us the vertex position. Now this vertex shader will run once for every single vertex on screen. You saw how many vertices in Blender were on a cube. That's 1, 2, 3, 4, 5, 6, 7, 8. And Minecraft has a lot more than one cube. So there's going to be tens of thousands at least of vertices that are being rendered. That means this code we write here will be run tens of thousands of times at least. Luckily, the GPU is fantastic at doing things in parallel. That means it won't run this code once and then run it again, and then run it again 10,000 times. It'll use all of the threads it has to run this in parallel. So every vertex gets its own physical thread to run this code on. That's why GPUs are so good at graphics. Anyway, let's do something. GLPosition is the output that is expected from the vertex shader. We can for now set that to vaPosition. GLPosition is expecting a vec4. It includes the XYZ, but it also includes a fourth, which is used for a variety of different things, but in this case, will be used for perspective. For now, we don't need to worry about that, so we're only going to put one. In the fragment shader, what does a fragment shader do? Basically, it runs for every single pixel on the screen. In between the vertex and the fragment stage, it assembles the vertices into triangles, and it determines which pixel will be covered by each triangle. The reason it's called a fragment shader is it doesn't actually run for every pixel, but for every fragment, which is basically a potential pixel. We might have multiple stages of this, so this specific fragment might not actually be output into a pixel. Only the final stage will output to a pixel. But basically, a fragment is a pixel. It's easy to think of it that way. We don't need to have this stuff from our vertex shader, but what we need to output is a color. The output that is expected is read by Iris or Optifine in a comment where we say draw buffers 0. A buffer is just a place to store something, basically. And we're going to store the color. Then we say layout location equals 0 out vec4, and we can name this whatever we want, but I'll use the traditional out color 0. This is where we'll output the final color for this part of the shader. And let's set out color 0 to be vec4 1. This is a vector 4 of red, green, blue, and alpha values. The colors will be mixed together to create the final color. In this case, when they're all set to 1, the final color will be white, and the alpha value will be the transparency. In this case, the 1 will mean it's opaque. Make sure to hit apply. Let's see what our beautiful shader is going to do now. And would you look at that? We get a weird white thing. That is actually our sword. If we switch to a different block, we'll see the shape changes. The reason it looks so weird is it is in entirely the wrong space. Not only are we only rendering a white color, but the vertices start in model space. Model space is the space that you would be in when you're designing a specific model, where 0, 0 of the coordinate system is centered on the object. Later, when you're putting this object into the world, and you might have multiple objects, you might have one object here, all in different places in the world, and this would be world space. You can also have other kinds of spaces that are kind of transitions between the two. The way you can convert between these spaces is by using matrices. 3 Blue 1 Brown is a fantastic series on linear algebra if you want to go into the specifics, which I recommend highly. But we can just basically use these matrices as magical space transformation things. This wonderful little sheet from the Shader Labs Discord is extremely helpful in helping convert between spaces. We will start in model space, and a vertex shader will expect the output to be in clip space. So we need to convert from model space to clip space. The way we do that is with a model view matrix to convert to view space from model space, and then a projection matrix to convert from view space to clip space. The chart uses an older kind of matrix from an older style of GLSL, but the one we will use is the newer one specifically built into Optifine and Iris. So let's go ahead and grab these two matrices and let's place them right here. Now first we need to multiply by the model view matrix to convert to view space, then we multiply by the projection matrix to convert to clip space. Now let's see what our shader looks like. And would you look at that? Everything is white. It looks like we failed, but we've actually succeeded. This means everything is being rendered, and it's all in the proper space, even the sky. That's why no matter where we look, we still only see white. So let's try to see something that's not white. Now this is very simple. We need to get the UV coordinates of the texture of every block, and that will be stored in vaUV0. Now, for the first time, we're going to need to pass some data from the vertex shader to the fragment shader. And what this will do is interpolate that data depending on where it is in the triangle. So if this vertex has some data, this vertex has some data, and this vertex has some data, and then the fragment, or the pixel, falls here, in between the vertex and the fragment, it will automatically average that data between all the 3 vertices. So for example, if this is red, this is blue, and this is white, right here you'll get reddish, bluish, white. Such a great color example, I know. So to pass a value from the vertex to fragment, all you have to do is say out vec2, because this will be a vector 2 with only 2 values, and let's name it text coord, which just stands for texture coordinate. Since each model of an object, in this case each block, is not just one singular color, the texture coordinates will tell you what color each part of the block is. For example, the top of the grass block will be green and the sides will be brown. The texture coordinates will be used to look at an atlas, which will have every single texture in the game and tell us where to look to find out what color one specific part of any object is. So let's just set text coord equal to VA UV0. To grab that data in the fragment shader, let's say in vec2, not 3, text coord. Then instead of making the color just 1, let's read the color from a texture. So let's use this texture function, which reads a color from a texture, and let's input the texture coordinates. To get the actual texture we need to read the color from, we use the built-in uniform sampler 2D, which is just a fancy way of saying texture basically, G texture. And that is the name of where we get the color textures for all objects in the gbuffer stage, which I'll explain what that is later. So let's put that in, G texture, and we should have some colors. Would you look at that? We do have colors, for some things. Terrain looks kinda weird right now, but everything else is rendering just like vanilla, except for the sky tube. Let's work on the terrain. The reason terrain is so weird right now, its vertex position arrives in a slightly different space than everything else. So let's go ahead and copy our gbuffers basic, paste it, and rename it gbuffers terrain. Now all we need to do different is get this extra value, uniform vec3 chunk offset. By the way, the difference between a uniform and an in is that these are attributes, which are specific to the vertex. And these can be more general values, which are also passed in from the CPU side. So now that we have the chunk offset, let's just add that to the VA position for terrain. And if all goes well, look at that. We have some rendering. What a start, right? There's still some definite issues here, mainly with transparency, as you notice. Grass that has transparent parts of the texture does not register that that part is transparent. Also, grass doesn't have a color. But while we have something kind of cool here, I want to show you what you can do with vertex shaders. Grab another uniform here. Let's grab the camera position. This will give us the position of the actual player in world space. Now using our handy chart, since it's in world space, let's convert our vertex positions also to world space. So first we need to multiply by the model view matrix, then we need to multiply by the gbuffer model view inverse matrix, then we need to add the camera position. So let's grab the gbuffer model view inverse matrix, and we already have the camera position. So let's take this part, also multiply by the gbuffer model view inverse, and add the camera position. And then we'll get a vec3 world space position. The reason there's an error here, this calculation gives us a vec4. We only need a vec3 for the world space position, so we can use what's called swizzling, which is just writing XYZ. And there, we just get the X, Y, and then the Z coordinates. And you can see we're still getting the error. And this is something I missed out on. The camera position is also a vec3. So we need to convert to a vec3 before adding the camera position. But now, there we go. Now what we want to do is create a distance from camera value. Then we'll simply find the distance, this is a nice built-in function in GLSL, between the world space vertex position and the camera position. Then what if we offset the position by just a little bit depending on the distance from the camera? Do you know what this will do? And would you look at that, we have a curved horizon in Minecraft. Now, the farther everything gets away from the camera, the lower down it is. And that creates a curved perspective to the world. This is how shaders can create a curved world in Minecraft. You might notice some floating entities and a magical chest. And that's because we only did this for the terrain. So all the vertices for the mobs and everything else still are not being influenced by this. That's why they're floating. For a comparison, again, here we have vanilla Minecraft. Here we have the curved surface of the world. This is kind of crazy, but you can always make the effect much less noticeable. Let's say 0.01. And there we go. Now it's just a slight curve as you get far away. Maybe a little more noticeable as you go up into the sky. For now, let's go ahead and remove the code that we used to add that curve. You can always add that back later if we want. And you might notice another little issue here. We have the exact same code in two different places. And that can lead to a lot of bugs. Say you change something with this code and you forget to change it for this code, and that could lead to a lot of errors down the line. So that's where we can use the include directive. If we just copy this text here, create a new file, and let's name it basic frag.glsl, or anything. You can name it anything you want, but just include GLSL at the end. Then we just paste that code. Then instead of including all this code, we can just write include basic frag.glsl. And there we go. Now when it sees this, it basically looks for a file called basicfrag.glsl, takes this, copies it, and paste it in here. We can write that same include statement here as well. And then we only have one file to change everything. So what exactly are G-buffers? The G in G-buffers stands for geometry. And buffers, as I said, is a way to store something. So it's a place to store geometry. These stages of the shader are called G-buffers because they run on the geometry itself. There are other stages like the composite stage that doesn't run on the geometry of the scene, but rather runs on the output of the previous stage after all the geometry has been processed. The output is usually things like colors or normals. You might also notice our distant horizons are not appearing, and that's because you do need to add an extra little bit to the shader, but I'll get to that soon. For now, let's try to get this shader to be able to render vanilla Minecraft just the way that vanilla renders it. Then we can start layering our own effects on top. So to get started, let's fix the most obvious issues, being the grass color and the grass lack of transparency. And the same with glass. We got a grass and a glass issue. Let's add some transparency to things. To do this is pretty simple. In our basic frag, the vec4 that this gets will include a transparency value in the fourth component. So if we say vec4 output color and assign it to that early on and then output the output color later, but we say if output color dot A, which is that transparency, it goes RGBA, the fourth component. If it is less than 0.1, which means that it is very transparent, discard. What this will do is discard a fragment if it is a transparent one. The reason this works is if there are a bunch of triangles in your scene and some are in front of other ones, the way that it renders, it doesn't actually know which ones are in front until it renders them. So the way it tells whether one is in front of another is with a depth value. But this doesn't allow for transparency. The way we add transparency is if the texture that we get using this method for one triangle, let's say this one is in front, if the texture is transparent here, then it will discard that one. Instead, you'll only see the fragment that rendered below it, which would be this triangle. Hopefully my bad art can help explain it. And if we go back and we check that out, look at that, we have transparency. As simple as that. Works for glass, works for grass, even works for water. Now let's make the grass not so gray. The reason the grass is gray is that the color of the grass changes depending on what biome you're in. So Minecraft stores the color in the vertex. So let's say in vec3 va color, and let's output that vec3 foliage color. Then let's set the foliage color equal to va color. Then in the basic frag, let's say in vec3 foliage color, and let's multiply our color by that. Ah yes, again we have the vec4 to vec3 issue. To fix that, let's separate our output color into a vec3 output color. Let's name this one output color data since it includes both the color and the transparency. So let's say the output color is the output color data.rgb, the RG and B channels of it, and that'll be times the foliage color. Then to make things more clear, float, because it's only one value and it might have some decimals, transparency equals output color data dot A. And let's just put transparency here to keep things nice and neat. When we're doing the output, let's make another vec4 of the output color, which is now altered by the foliage color, followed by the transparency, which together will make a vec4. And if all that was done correctly, we failed. It looks like we succeeded, but there's actually an error because we have this code included in both GBuffers Terrain and GBuffers Basic, and we didn't even get the color in GBuffers Basic. So we just got to get the color in GBuffers Basic too. So let's copy some of that code over there. Get the VA color in GBuffers basic. And now we're actually sending a foliage color for it to get. Still an error. This does happen sometimes. It's really hard to find out what the issue is when it's something like this. I don't know what this means. You think of what did you change last. Sometimes you can undo things and just see when it breaks again. Back when we were here, it worked. So now let's change things one at a time and see what breaks it. Oh, you know what? Did I misremember? Vec4 VA color. That's the... Oh, you gotta love Minecraft shader bugs. We did it. We got through it. We figured it out. So we just do VA color.RGB. Just the RGB. That's all we need. Let's do that for both of these. All right. Now, if all went well, we should have colored grass. And we do. The way you can tell that it works is it says shaders reloaded and no errors. Well, would you look at that? This is our shader, but it looks like normal Minecraft. Well, almost. Look at the sky. You see that? Iris does not include totally vanilla skies, so the way to fix that is to do the skies a little more manually, but we'll keep it easy. Since this is just a way to replicate what vanilla already does, I think it's alright to use a template for this. In dev info on Shader Labs, there are a bunch of wonderful templates here. This is the one with the newest version, and we are looking for GBuffers Sky Basic. We just gotta grab these files and let's make GBuffers, don't forget the GBuffers, Sky Basic.vsh, copy, rename Sky Basic.fsh. The VSH will be this, and the FSH will be this. Just for compatibility reasons, let's change the version to what we have. This uses compatibility, so it's able to use some of the matrices that are used with the older version of GLSL. Ftransform is a built-in function that does the exact same thing as projection matrix times model view matrix. What's interesting here is GL color is another old thing, but it basically is the VA color. It's the vertex color. For the sky in Iris, it stores star data. So it stores whether or not there is a star, stores the star color. This is basically a conditional expression to test whether there is a star or not based on the vertex color. What this does is it adds some fog, just like vanilla, and it calculates the sky color based on the direction. This is just a space conversion function. It outputs the color and the stars. So if we look at what that does, would you look at that? Now, the sky looks much more vanilla. Let's also look at night versus vanilla and not vanilla. Yeah, there's actually no lighting right now. You especially notice at night. Since it's nighttime in vanilla, things are brighter if they're next to lights. In our shader, we don't have any lighting implemented right now, so everything's the same brightness all the time. So let's get to work on adding lighting. Here we can see the light map is stored in VAUV2. This is the light value that vanilla calculates for every block. It calculates it based on the sky light and the block light from torches and things like that. So let's have in IVEC2 VAUV2, and IVEC2 is the same as a VEC2, but it uses integers instead of floats. And an integer is just a whole number, like 1, 2, 3, 4, instead of 1.2834, like would be in a float. So let's pass this out. The reason I'm calling this light map coordinates, not only does this store how bright the value is, it also stores what color it is. And it does this by accessing a texture that has every different color that's used for lights in Minecraft. So let's set the light map chords to VAUV2. Basic frag, let's get in the light map chords, and we're going to be accessing another texture for this. We're going to get a light color. So let's say light color equals, and the texture that this will be stored in is light map. Nice and simple. Let's access light map, but not with the normal texture coordinates, but the light map coordinates. And we got to remember that texture returns a vector 4, so we'll need to make that a vector 3. Now we have the light color, and let's just multiply that by our color to change the color of every block based on the light. And let's see what that looks like. And it crashed. In basic frag, we're passing in the light map coordinates, but we use basic frag for GBuffers basic, which does not send out the light map coordinates. So let's just make sure to add the light map coordinates to GBuffers basic. You might notice we're doing a lot more copying and pasting between GBuffer's basic VSH and GBuffer's terrain VSH. There's not much that's different between these two. There is something, the chunk offset, but that's not much. So I'm going to show you a little trick. Let's just pretend that the chunk offset would work for everything just for now. Let's create a new file, basic vert.glsl. Let's paste our terrain VSH in here, and in GBuffer's terrain, let's hash include basic vert.glsl. That's why it's not working. Little typo there. Let's do the same thing for GBuffer's basic. Now the reason this works is that chunk offset is simply going to be 0 for anything that's not terrain. Here's something helpful when you mouse over an error like this. It says that the error is from GBuffer's terrain.vsh. So I accidentally put basic frag instead of basic vert. Copying and pasting, it's gonna kill you, but it's also really nice. Use at your own risk. Uh-oh, it crashed again. Well, that might be an issue. We're taking an iVec2, which is an integer vector, and we're trying to apply it to a texture. Expects a normal vector to, not an integer vector. So we can go ahead and convert light map chords to a normal vector too. Fortunately, crashes don't happen too often. Usually, you can actually just see an error in the game. No! Okay, when in doubt, undo until it works. When you see OpenGL does not allow include directives, that means that, not what it says, that means that it actually just can't find the title you typed here. And the reason it can't find it is because I accidentally undid my typo in the name too, so. Oh, I know what it was. So when you have an integer, do you remember how I said when there's a triangle, there's different values for each vertex, and for a fragment, it interpolates between those values? Well, for an integer, if you just have 2, 1, and 3, it can't average between these for an integer because there are no decimals. So what you have to do if you want to pass an integer from a vertex to a frag, you have to say flat. What that does is it stops the interpolation, and it just passes directly to the frag. Now you only want to use this when every vertex has the same value, not a different value. Because if they have different values, then it's just going to be whatever vertex happens to run last is what ends up writing to this, and the other values will be ignored. But that doesn't matter. If every vertex has the same value, then you pass it correctly to the fragment. So what we need to do is not just out iVec2 VA UV2. We need to do flat out. Did you ever play that game? That was a good game. Anyway, I put in. Why did I put in? Okay. And not VA UV2, light map chords. You can't reuse a name. And there we go. Light map chords equals VA UV2. And then let's make sure we're taking that in over here. And we also have to have flat there. So flat in light map chords. And before we do anything with it, let's make sure we didn't mess up horribly. And we did not. Now we can do what we were doing earlier. Then light color times our color. We need this to output a VAC3 with RGB, but it does not look right. I simply forgot a space conversion. Now what these numbers do, these just get the number from the range that VAUV2 comes in, which is a range that's useful to vanilla Minecraft, into a range that we can use between 0 and 1, which is good for accessing a texture. The reason there's this issue here is these numbers involve floating point numbers. So what we're actually going to do is take light map chords, change that to a normal vector. Then we don't need the flat anymore. And yes, that means we never needed to add the flat in the first place. But I left it in to teach you about how flat works, and it's also useful to see mistakes. That way you can see how to work your way out of them. And now, oh no. So apparently, if you have a capital M in lightmap, then you're not actually accessing the lightmap, you're accessing who knows what. Nothing good. That just took me 30 minutes to figure out. Anyway, lighting. This may look like vanilla Minecraft, but this is our shader. Let's toggle vanilla, our shader, vanilla, our shader. Now with our shader, we have light near light blocks. We have darkness depending on what time of day or night it is. And if we go into a cave, then it will be dark except for block lights. Another thing to help make the colors look more like vanilla is we need to convert the colors to a different color space. The way we do that is we just set it to the power of 2.2. And since this is a vec3, we need to do vec3 2.2. All this does is change it to a more linear color space. You don't need to worry quite about what that means, but basically it makes it more accurate for us to do lighting calculations with it. And then we undo what we did before by putting it to the 1/2.2 power. So we just do that on every color input. So our light color, we do it to our output color data, we do it to our foliage color. The only difference in the lighting right now is vanilla applies some tints to different sides of blocks just based on which way they face. But we won't add that because we'll be doing much more complex kinds of lighting pretty soon. Last thing to add to transition everything to look like vanilla is distant horizons. First thing to do is create a new file and name it DH terrain VSH. Copy and paste, and let's name this one vhterrain.fsh. Now what would happen if we just take our basic vert and our basic frag and add those to DH terrain? Let's see. We have an issue. Looking at ShaderDoc, which is another great website for help with shaders, it has a section specifically on distant horizon support for iris, and here we can see that these are the only attributes that we can use. Now the only matrices that are supported are the older built-in versions, so we will have to use the compatibility mode of GLSL. So let's copy what's in our basic vert and make it into a compatibility version. The older version of GLSL has a really simple way to have a projection matrix times model view times the vertex position, and that is just a little shortcut function called ftransform. Here's something cool as well. If you want to, you can go ahead and use the compatibility mode in the basic vert too. Alright, so for compatibility, we don't have VA color, does not exist, but we do have an alternative, which is GL color. For distant horizons, this is not just going to be the foliage color, so I'll rename this. This is just going to be the block color. Now there's not going to be any texture coordinate because there's no textures on blocks in distant horizons. Once again, we are trying to put a vec4 into a vec3. Let's just make the block color a vec4 because this does have important transparency data. To get the light map chords in compatibility mode, we will use this, which is GL multi-text chord 1, basically a replacement for VA-UV2, and this needs to be changed spaces. Remember how we change spaces by multiplying by these numbers? It has a built-in matrix to help it change spaces to the correct space. And then we only need the first two components because those are the only important ones, so we do .xy. And now we have our light map coordinate. Let's copy our basic frag, put that into distant horizons terrain. We're not outputting the texture coordinates anymore, so we only have in the block color and the light map coordinates. The reason we have an error here is we don't have a texture coordinate, so instead let's have the output color data be equal directly to the block color. Now the foliage color does not exist, that's included in the block color. Yes, we forgot to delete our model view and projection matrix and chunk offset, which we don't need. And we also cannot access the VA position. There we go. Make sure we're not trying to access any things that don't exist for distant horizons. I found the error. This is not supposed to be GL multi-text chord 1, it's supposed to be GL multi-text chord 2. 1 does not exist, and this needs to be the texture matrix 2. How did I forget to delete this? This does not exist either. We need to make sure we set the fragment shader to compatibility whenever we set the vertex shader to compatibility. So now, there we go. Distant horizons is working. Well, almost. We see distant horizons water through our terrain. Not quite sure why this is, but we need to do a manual depth check for all distant horizons water. We don't have this issue with distant horizons terrain. Quick side note, a thing we can do is change the color space of the distant horizons terrain so it stops looking so washed out. We just need to apply our power, which changes to linear color space, to the block color, and that's much better. To prevent the distant horizons water from appearing in front of the normal blocks, we will have to check the depth. Let's get the uniform sampler 2D depth text 0. Since this is a texture, we will need a texture coordinate to access it. Now this texture coordinate won't be like the texture coordinates we got before from the vertex stage, because this one just needs to access things based on where they are on the screen. So to get a coordinate that ranges from 0 to 1, depending on where you are on the screen, we can use the built-in variable GL_frag_xy. However, this doesn't go from 0 to 1, it goes from 0 to 1920 by 1080, or whatever the resolution of your monitor is. So what we can do is divide this by vec2 view width and view height, which is the resolution that Minecraft is running at in game. And we can pass both of these in as uniforms as well. Uniform float view height, uniform float view width. Now we have a texture coordinate. So let's get the float from the depth text 0 texture with our new texture coordinate. The depth is stored only in the first channel, so the R channel. Now that we have our depth for normal blocks, we just need to check if the depth of normal blocks is not equal to 1.0. That means the depth is not the maximum, so it's not the sky, which means there is a normal block there. And if there is a normal block there, we will discard the distant horizons block, so the normal block appears in front. And there we go. Now it looks much more like vanilla Minecraft. Last thing we need to do to complete the vanilla look is add the fog to distant horizons. Fortunately, we have a uniform vec3 fog color. Now we can use the mix function, which will allow us to mix between the output color and the fog color based on a fog blend value that we will define later. So whenever fog blend value is 1, we will get the fog color, and when fog blend value is 0, we'll get the original color. We only need to do this in distant horizons terrain, because fog will only be really far away when distant horizons is enabled. So let's define the float fog blend value, and let's set it to be based on the distance from the camera, because the depth won't extend far enough for us. So let's find the float distance from camera as the distance between the view space position of the player and view space frag position. First of all, we know the view space player position is actually just a vector 3 of zeros, because view space is defined as where the camera is at the origin. So all we've got to find is the view space frag position. So let's get the vector 3 view space frag position. Calculating the view space position is going to be pretty simple. Let's just go back to our distant horizons terrain VSH. We'll send out the vector 3 view space position of the vertex, which will be interpolated across each triangle, so it'll be correct for each fragment. And to calculate this for the vertex, we'll have to take a look at our handy sheet. And even though this does not say G buffers in front of it, it's still in the same category because it runs over the geometry. In this case, the distant horizons geometry. We'll use the old matrix, GL model view matrix, and the old vertex position, the modern equivalent of which is VA position, and make sure that's a vector 3. So we'll do GL model view matrix times GL vertex.xyz. Then we'll just grab the in vector 3 view space position. We don't even need to define that now. Let's just use it here. And let's make sure to actually assign this mix value to the new output color. Now we want the fog blend value to go from 0 to 1 as the distance from camera goes from the max value to the min value. So let's just quickly set a max fog distance. Let's try 500 and a min fog distance and try 200. To get distance from camera into the proper range, we need to first subtract by the min fog distance so that the fog blend value is 0 when the distance from camera is the minimum fog distance. Then we just need to get it into the right range, so we will divide by the max fog distance minus the min fog distance, which in this case will be 300. 500 minus 200. We do that so that when distance from camera is 500, first it's subtracted by min fog distance, then we get 300, and max fog distance is also subtracted from min fog distance, so we get 300 there. 300 divided by 300 equals 1. And that's the start of our fog. Let's just get those values better with trial and error. Also real fast, gotta remember to do that color space conversion. Let's just take this fog color and set it to the power of vector 3 2.2. And one extra thing we need to make sure of is we need to clamp this fog blend value in between 0 and 1. We need to do this because otherwise, when distance from camera is below 200, we'll get negative values for fog blend value, which is not what we want here. And if it's above 500, we want it to stay 1 and not be 2 or anything crazy like that. And there we go. Now the fog actually blends into the horizon, but it's so aggressive we can't even see our distant horizons. So let me just change that. If we compare our distant horizons to vanilla, we can see that vanilla's fog is actually extraordinarily aggressive and actually makes you miss out on a lot of the distant horizons. A value that I found to be pretty good is 4000 to 2500. Now you get a nice fade out for the really distant things, but you can still see pretty much everything compared to vanilla. Now unfortunately, that's all we have time for in this video. I know we didn't really get to the exciting stuff, but we really set the foundations. From here, it's not going to be too hard at all to start doing complex lighting effects, but next video, we're going to go into reflections, we're going to go into shadows and colored shadows, we're going to integrate resource packs and add different kinds of lighting depending on different materials, using PBR, which is physically based rendering, so look forward to that. I hope you enjoyed the video. If you really enjoyed the video, then it would be amazing if you could support me on Buy Me a Coffee or with a YouTube membership. That'll help me make more videos, and I'll see you in the next video.